Hello, everybody. I'm here to go through your review for our next unit test, or the second part of our unit test that is all about exponential and logarithmic functions. I've got on this first screen the three formulas that we used with respect to exponential growth and decay. You will have them available to you on the test as well, so you don't need to have them memorized, but you do need to understand what each of the parts of each function represent. So for example, the a value is always going to be the initial amount. The r value is always going to be the annual percentage rate. But remember, you must change it to a decimal. Okay, t is always going to represent time. And usually you'll see it measured in years, but it doesn't necessarily have to be years. The value n here is only used when we're using our compounding formula, and it's only for exponential growth. Even though there's a plus or minus symbol in here, it's actually always going to be growth. And n represents the number of times interest is compounded in a year. And it's really only for interest. It's really a financial formula, so it's really only used when we're dealing with interest that's being compounded, either in terms of a debt that you owe or interest that you're earning. So if you ever see something as compounded, quarterly, or compounded annually, compounded monthly, that's when you're going to use the n formula. Anytime you see something called compounding continuously or constantly, that's when we're going to use our base e. And remember, e is the natural number. And it's approximately 2.72. So it's not a variable. It's like pi. It's an irrational number that just occurs naturally. If I were to take this base here, my 1 plus or minus, or actually just the 1 plus r over n, and raise it to the n power, and suppose I, for example, put in an interest rate of 100%, as n increases towards infinity, that quantity will approach 2.72. That's one of the exercises we did at the beginning of the unit. Okay, let's go ahead and start talking about the review. The first question is asking you to complete a table about the key features of a logarithmic function. Well, if you remember, when we talked about the parent function, all logarithms have what we call a vertical asymptote. And so that's essentially what a logarithm looks like. And all logarithms have a vertical asymptote. All logarithms are going to have a domain that relates to the vertical asymptote. And the range for every logarithm is always going to be all real numbers. And like I said, all logarithms are going to have a vertical asymptote. And the vertical asymptote is going to depend on the value of h when we start transforming the equation. If you remember, we have y equals a is going to be where we start, and then we have the log of x minus h plus k. Well, the a is going to be your reflection and your dilation of the graph. It's not going to affect your domain or range, since your range is all real numbers. But the value of h, because it shifts the graph left and right, is going to impact your domain. And so our domain is always going to be x is greater than h. H also happens to be our vertical asymptote, and so our vertical asymptote is always going to be equivalent to h. The value of k shifts the graph up and down, which would normally impact our range, except since our range is all real numbers, whether I shift the graph up or down isn't going to change the fact that it's going to cover every number along the y-axis. So let's take a look at the first example here. I'm just going to go ahead, since the value we really need to figure out is the value of h, I'm going to look inside the parentheses here, and I can see that x is alone. That tells me, that the value of h is 0 here. And so my domain is going to be that x must be greater than 0. We already know that the range for every logarithm is going to be all real numbers, and the asymptote is also going to correspond to 0. I'm going to come back and do the x and y intercepts in just a minute. Let's finish filling out the rest of this table for the other functions. So my function g of x, if I look inside my parentheses, I see x minus 2. Well, remember, The formula itself is x minus h, and so if you remember, the sign is always opposite the value of h. So h in this case is actually a positive 2, even though you see the subtraction sign in the equation. That's because there's a subtraction sign in the formula. So if h is 2, that means my domain must be that x is greater than 2. My range, just like all logarithms, is going to be all real numbers, and my vertical asymptote is going to correspond to the value of h as well. And finally, I've got my h of x function, and again, the a value in this case is negative, but that doesn't affect anything. It doesn't affect my domain or my range, so I don't even have to worry about it. All I need to do is identify the value of h. And since in parentheses I have x plus 1, that tells me that h is actually a negative 1. So if you can remember inside opposite, the k value is always going to be moving the graph in the same direction as the sign. The domain in this case then would be x is greater than negative 1. The range is going to be all real numbers, and the vertical asymptote is just going to be x equals negative 1. So when it comes to finding the x and y intercept, this is where it gets a little bit tricky. To find your x-intercept, and this is true for every function, not just a logarithm, we are going to let y equal 0. To find the y-intercept, we let x equal 0. The y-intercept is actually a lot easier to find. So let's actually do that first. To find the y-intercept, since all we're doing is plugging 0 in for x, I can do that on the home screen for each of these equations. So for f of x, I'm just going to type in 2 times the log, and since there's nothing else in the parentheses except for x, I'm going to plug in 0 for x, and then I've got plus 6. And that'll tell me that there is no, when I get an error message like this, it tells me that there is no y-intercept. And that's because if this function, f of x, has an asymptote at x equals 0, that's just the y-axis, which tells me that my graph never crosses or touches the y-axis. So there is none. There is no y-intercept. And I'll show you on the graph. If I go ahead and go to my y equals screen, I guess I have to clear that. All right, if I go to y equals and I type in this function, 2 times the log of x, and close my parentheses before adding 6. Okay, I'm just going to do this on a standard window, which is zoom 6. And remember with the logarithm, because that vertical part of the graph is so steep, our calculator doesn't always show it very nicely. So it's a little bit hard to see, but I can tell that the graph doesn't ever cross over the y-axis. If you can remember that the vertical asymptote is the y-axis, then that should help you understand that there is no y-intercept because the graph never touches the y-axis. It does, however, touch the x-axis. It's just really hard to see. If I want to see where it touches the x-axis or find the x-intercept, I have to go in and let y equal 0. So I'm going to suggest putting in another equation where y equals 0. Go back to your graph. Now you're not going to be able to see the line y equals 0 because it's going to be on top of the x-axis. So you're just going to have to trust me that it's there. To find the point of intersection now, if I go to second trace, I can now use the intersection option and find the intersection between those two curves. Now the only problem with the log, notice where it's asking me for my first curve, and right now my cursor is at x equals 0. Well, my log function never hits 0, so if I try to press enter, it's just going to keep giving me, it's going to keep asking for the first curve. Notice how there's nothing listed for your y value. Now that's because the cursor isn't on my graph yet. So I have to press the right arrow to move the cursor onto my graph. Now you can see that there's an x and a y value. The cursor's clearly on the function, and I can press enter, and now it'll ask me for the second curve. Well, the second curve occurs when y equals 0, so I'm just going to press enter again. We ignore the fact that the calculator asks for a guess, and we press enter until we basically see the intersection. Now this x value here, 1e negative 3, is the same as 1 times 10 to the negative 3. And you're going to see a lot of scientific notation on your test, so I just want to make sure that you're comfortable with what this means. Basically means if I have 1, that's like 1.0, I would move my cursor 3 points to the left, or 0.001. If I move this cursor, or if I move my decimal point 3 places to the left, I get 0.001. I want to be careful of calling it 0 because it isn't exactly 0. It's going to be 0.001. To find the x and y intercept for my next function, let's just go ahead and type in the new graph, or the new equation. I'm just going to type over And this is going to be x minus 2. Parentheses. Okay, so let's just take a look at the graph. So I can see that it's been shifted over a little bit. Again, it's very difficult to see the vertical part of the graph because it's just not, the calculator's just not able to define that part of the graph very clearly because it's not a high-def calculator. But I think it's also pretty clear that this graph is never going to cross the y-axis. I have a vertical asymptote at x equals 2. And so my graph is never going to cross the y-axis. So I'm not, in this case either, going to have a y-intercept. But I can see that it crosses the x-axis. I've already got my second equation for y equals 2. So at this point, if I go second trace, I can choose my intersect option. And notice again, I've got the situation where my cursor isn't on the curve yet. So I have to press my right arrow, and you can see the value. There we go. You can look at your values of x to see kind of where your cursor is. Once your cursor is on the function, you can press enter, enter again, and finally your intersection occurs when x is equal to 3. Now that is your x-intercept. And the last one, we have y equals h of x, h of x is equal to negative log. So I'm going to insert a negative, and then we've got x plus 1. Let me fix this, plus 1, and then on the outside we have minus 2. And this I can see very clearly. It crosses the y-axis. I can't see very clearly where it crosses the x-axis, though, because the graph is too steep to show. But to find the y-intercept, this is where I'm just going to let x equal 0. There's another area, or another way that you can find the y-intercept using your calc menu. Instead of choosing intersect, we can choose the value option, and if you press enter, you can actually substitute in values for x, and the calculator will determine them for you. So if I let x equal 0, I find that y is equal to negative 2. That's my y-intercept. If I want to find the x-intercept, I'm going to go back and make sure that I have the 0 in y2. Go to second trace, intersect. Notice that my cursor is on my function, so that's fabulous. I'm just going to press enter 3 times until I can see the point of intersection, and that occurs when x is equal to negative 0.99. Okay. The next set of problems, you're given a function, or you're given a part of a function, and then you're given a point, an ordered pair on the graph, and you're asked to figure out the missing piece. So for example, in f of x, we're given a times the log of x minus 2 plus 5. We're told that when f of 12 is equal to 3. Basically, this information is an ordered pair. It gives us the ordered pair 12, 3. And so if we've got the ordered pair 12, 3, that gives me a value for x and a value for y. If I substitute that information into the equation, then I can figure out the value of a. So remember, f of x is the same as y. So if I plug in, I'm going to plug in a 3 for that side of the equation. I don't know the value of a, so I'm just going to leave it there. And then I've got the log, and in parentheses, I'm going to substitute in the 12 for x, 12 minus 2 plus 5. And now I'm just going to use my order of operations and simplify. So if I take a look at this, this is 12 minus 2. If I look at my parentheses, that just gives me 10. So I have a times the log of 10 plus 5, and that's still equal to 3. Well, the log of 10 is something that I can actually evaluate on my calculator. If I go to my log button and press 10, I find that the log of 10 is just 1. Well, remember, here is just multiplication. Since I'm multiplying a times the log of 10, and I just figured out that the log of 10 is 1, this equation basically boils down to this. 3 is equal to 1 times a, which is still just a, plus 5. Now this is just a linear equation. If we subtract 5 from both sides, we get that a is equal to negative 2. We could do the same thing for letter B. This time, though, the missing term is the value of k. But again, I'm going to substitute in negative 2 for x, and coincidentally, I'm going to substitute in a negative 2 for y. So let's see. Negative 2 is equal to 3 times the log of negative 2 plus 3 plus k. All right, so basically what I want to evaluate is the log of negative 2 plus 3, or basically the log of 1. Since negative 2 plus 3 is just 1, I'll just type in the log of 1, which gives me 0. So what I have now is negative 2 is equal to 3 times 0 plus k. Well, 3 times 0 is just 0, so k is equal to negative 2. All right, and then finally in letter C, it's the same thing as before. We're trying to find the value of a. This time x is 19 and y is 5. Whoops. I should say y, sorry. All right, so 5 is equal to a times the log. And then I've got 5 times 19 plus 5 minus 1. So I want to figure out what that log of 5 times 19 plus 1 is. So I'm just going to actually type that all in at once. 5 times 19 plus 5, and I get 2. So I find that 5 is equal to a times 2 minus 1. Well, we're not used to seeing it a times 2. We're actually used to seeing it as 2a. So I can just rewrite it as 2a, and then I'm solving another linear equation. If I add 1 to both sides, I get 6 is equal to 2a. If I divide both sides by 2, I get that a is equal to 3. And one of the ways that you can check to make sure you've done it right is to go into your y equals and type in the equation with the value of a. So if I type in 3 times the log of 5x plus 5, and close my parentheses, and then I've got a minus 1. What I can now do is go to my table. If I go to second table, I can look to see if what happens if x is 19, does it really show me a value of y that's equal to 5? So if I scroll down, I can see that when x is 19, y is 5. All right, in problem number 3, here we're given information about the value of a car that can be modeled by the function v of t, which is equal to 18,000 times 0.875 raised to the t, and t represents the age of the car in years. So if I want to know the value of the car when it was initially purchased, that's when I look at that initial value, my a value. You want to make sure that you're using appropriate units, and in this case we're talking about money, so the car was originally $18,000. The next question is asking if the value is increasing or decreasing. In this case, because my base is less than 1, I know that it's decreasing. But this is where you have to be careful, because it's not decreasing by 0.875. That's the percentage that remains. So 0.875 is the same as 87.5%. That's the value that is left. So if I want to figure out the amount that it decreased, I'm just going to subtract this from 1. So if I do 1 minus 0.875, you can do this on the calculator. We get that it's 0.125. And remember, if we want to write it as a rate, then I'm going to want to write it as a percentage. That's going to be 12.5%. If I want to figure out the value of the car in 8 years, I'm going to let t equal 8. And so we've got 18,000 times 0.875 to the 8th power. And we're told that the value of the car is $6,100, or I'm sorry, $6,184.96. Typically we want to round to 3 decimal places, but when we're dealing with money, it makes a little bit more sense just to round to 2. Okay. Number 4, another problem that deals with exponential growth or decay. Alexis currently has $957.71 in our savings account. Now, I forgot to add this part, so the paper that you have does not include that statement that says that she opened the account 5 years ago. So make sure that you write that down, because you need to know how long the money's been in the account. You're also given that the account pays 6.5% interest. So we do have to remember to change the 6.5 to a decimal, which means that we have to move the decimal place over 2 units to the left to make it 0.065. If the interest rate is compounded daily, what was her initial deposit? So daily means that we're going to have to use our formula that involves the n, and it means that n is 365. So if I want to figure out her balance, her original balance, there's a couple ways that you can do this. I can actually go back. I think it's actually easier to look at this as back in time. If she currently has $957.71, if I look at the compounding formula, it's going to be 1 plus, I'm going to have my 0.065 over the number of times that we've compounded, which is 365. And then my exponent is going to be 365 times the number of years that the money has been in the account. Since I want to go back to what it was 5 years ago, I can actually multiply by -5. And I can go back in time to see what her initial deposit was. Another way that I could do this is just to set the whole thing equal to $957.71 and then divide. I think this is a little bit easier though because you can do it all in one step. So if I take 957.71, and then in parentheses, I want to do 1 plus. Now be really careful because when you have a fraction, you have to put the fraction in parentheses. And you'll need to have 2 parentheses to close this off. One to close off the fraction, and then another parenthesis to close off the base before raising it to your exponent. Another thing to get in the habit of doing is making sure that your exponents are also in parentheses. If you have one of the newer calculators, it's not as big a problem because the calculator actually pushes the cursor into your exponent. It raises it up, but if you have an older computer or an older calculator, you do need to make sure that you have those parentheses in there. Okay, so it turns out that if this was the way her account was set up, that she would have had to deposit $691.99. In letter B, it says if her interest rate was compounded monthly, what was her initial deposit? So everything about this is going to stay the same, except instead of having 365, and is going to be 12. So I'll have 957.71. 1 plus, this is going to be 0.065, but now we're dividing by 12, and this will be 12 times -5. Now, the easiest thing on your calculator is to recall your previous command instead of trying to type that all the way back in. And then all I need to do is change my 365 and type over and make it a 12. So I'm going to type in a 12. I need to delete my 5. Then if I go into my exponent, I'm going to do the same thing. 12. And then delete that extra 5. And the values should be pretty similar. So we get 692, 50, that'll round up to 58. So the value should be pretty similar. If you get something entirely different, then you know you've made a mistake somewhere. Okay, I'm going to call this video part 1, and then I'm going to save a second recording to complete the rest of your review for you. So this is just going to wrap up part 1 of our review.